Good afternoon, everyone. My name is Prasanth Kothuri. I work at CERN. This is the Physics Research Center in Europe. I'm going to talk about how big data tools are helping us accelerate physics research at CERN. I'll give you a quick overview of what we are up to at CERN, and then I'll go through the tools that are pushing the frontiers of physics research. So CERN is a European laboratory for particle physics. So this was the place where Webb was invented by Tim Berners-Lee. Today it's home to what is the biggest particle accelerator in the world. It's called LHC, Large Hadron Collider. In the Hadron Collider, the particles are accelerated to the speed of light, and they are collided at 4 different points. And in each of these points, we have a big experiment. So the experiment, when I say the experiment, it means there is a big detector that is detecting the collision of these particles and collecting data. So these are called ATLAS, CMS, LHCb, and ALICE. It's a collaboration across many countries. So today we have what we call 22 member states and 6 associate members and several worldwide collaborations with research institutes, etc. So we have around 3,000 people who put together this LHC. And we have more than that, like 12,000 people who actually use our facilities to do the research. And we have around $1 billion francs per year to play with. So where are we based? So we are in the border of Switzerland and France. So the LHC, which is 27 kilometers in circumference, goes across Switzerland and France. We're in Geneva. So this is the largest machine in the world. So there are a lot of superconducting magnets that actually orient the beam so that it goes in a circular path. And this is the fastest racetrack on Earth. So the protons go at almost the speed of light. And since we want to understand what happens when the collisions happen, so there is absolutely no noise. So it's a very high vacuum place. Something is something is wrong with the sorry, let me exit and I can use this also. So we're back business. So as I said, it's the emptiest place in the solar system. So it's a very high vacuum place, so that the collisions are like what we want. So there is no noise. So when the collisions happen, it creates a very high temperature. So it is the hottest spot also in the galaxy. So at these 4 places, so you see the experiments, the LHCb on the top, ALICE on your right, and then there is ATLAS and CMS. So we have detectors. So these are particle detectors that detect the collisions and collect the data. So this you can imagine as like IoT sensors. So this data is initially filtered. We use what are called FPGAs to do the filtering, and then sent to the CERN data center. So that's why I mentioned the numbers about the CERN data center. So here the physics data is aggregated in the CERN data center where the initial reconstruction happens. So you can imagine each collision as an event, which is a big record. But when the data collection happens, we collect bits and pieces, and then these are reconstructed using our batch form and stored in our data center. So in addition, we also have a remote extension of our data center that is in Budapest, Hungary. So we collect when the LHC is running. Now it is in the shutdown mode, so there are maintenance work going on. But when it is running, we collect around 12.5 petabytes of data every month. Only a fraction of it can be analyzed because we are restricted by the amount of compute that we have. So as you see, we do not have we have around 200,000 cores, but that can only analyze around 2 petabytes of data. So when I say 2 petabytes accessed, it's mostly reading that. And if you wonder, all this data is actually stored in the tape. We also have some copy on the disk, but the long-term retention is in the tape cartridges. And if you see the density of tape, nowadays it can store up to 200 terabytes each tape. So in a broader view, you can classify data we have at CERN into two buckets. So what is called physics data. So these are the data from the collisions. For this, CERN has developed an internal framework to analyze this data. It's called ROOT. This is in the 1980s when there is no big data tools available. Today here we don't use a lot of open source stuff. So what we use here is a ROOT framework, which is internally developed. So we are trying to use Apache Spark, but it is in the early experimental stage. So I'm going to focus on the bottom part, so which is the infrastructure data. So this is the data that is coming from the IoTs in the LHC. And we also have a lot of data catalogs. So the people will catalog data saying that I'm interested in this data set. And we also use Hadoop and Spark to monitor our CERN data centers. So all the metrics and the logs are collected, various pipelines, and eventually ends up on HDFS. And it's also available for the users through various means like Grafana, Jupyter, and things like that, Kibana. Okay, so why did we choose Hadoop and Spark for big data analysis? So when initially the LHC was started, the luminosity was not that high. So luminosity refers to number of collisions that happen in a particular beam run. So as the years progress, the luminosity has increased, so which means the number of collisions have increased. So that means the amount of data that we could acquire has drastically gone up. So as I said, now it's in the maintenance phase, where the luminosity is going to increase further in the next year. So the data is going to increase further. So we cannot store all this in relational databases. So we need to, even if we are able to store, we cannot process it in a reasonable manner. So that's when in 2011, we were trying to see what is available. And we did some early prototype work with Hadoop and HBase. And we decided together with the team that is responsible for LHC data that we should give this a go. Today, the LHC Accelerator Logging project actually relies heavily on Hadoop HBase to store their data and use Spark to process their data. And we choose it for these reasons. As you know that we have multiple data processing interfaces, so it can operate at scale by design because you're not sharing anything in comparison with the engineered systems where you have InfiniBand or things like that. It can run on commodity type servers, so we can just buy x86 servers and it can run. And we have also many solutions that target data analytics and data warehousing. We are also interested in the stream processing, so we use Spark streaming heavily. And for machine learning, we don't we don't yet use Spark. What we use is mostly Keras and TensorFlow. And we also went because several people in the industry were using this, so there is a good community around Hadoop at that time. So just to give you an idea, this is the timeline. As I said, we did some early prototype in 2012. And then we first deployed our cluster in 2013. So we ran our cluster with Kerberos. And we had a big project in 2014, that is the monitoring of our IT infrastructure. And that's when we also migrated everything to Hadoop 2 that runs on Yarn. And we also started a little bit of Apache Spark in 2014. And we evaluated multiple solutions for SQL on, let's say, unstructured data. So we mainly use Hive, but we have used Impala in the past, but the usage has gone down recently. Nowadays, we are trying to see if Presto can help in this area. And then we moved on to having Kafka. And then recently we have a data science platform that is built around Jupyter notebooks. So internally we call it as Swan. So this is a service for web-based analysis. And we have done some testing the beginning of this year for Hadoop 3. And we plan to migrate to Hadoop 3 early next year, mostly in January. this is our, like, let's say, our production stuff. And nowadays we are also running Spark on Kubernetes. As you will see that not all of our data is stored on HDFS. It is stored on some internal CERN storage systems. So if we can decouple storage and compute, which Spark can help, and we can run Spark on Kubernetes on our internal cloud, this allows us for the elasticity of the resources. So I am part of the Hadoop and Spark service together with 8 other colleagues. So we set up and run the infrastructure. Not only that, we also heavily support our user community, because all these tools are not very easy for them to get started with. So we do a lot of consultancy, and we work with them in the initial prototype of the data pipeline or the project. And then we have a checkpoint to see whether to go ahead or not. And having this deployed is not enough, because people have to use it. So this is where we had a lot of challenges initially, that we had acquired a lot of data. We had a data lake, but it was not very easy to access this data and process this data. So this is when we pivoted a little bit, and we developed a data science platform around Jupyter notebooks, and then integrating with all the CERN resources, starting from single sign-on to making a Spark connection with a click of a button, and things like that. And our clients obviously can also, we provide some Docker images and our libraries. So this is how it looks in numbers. So we have around 6 clusters. So we run it on the physical servers for the most critical ones, but for let's say the reasonable, for the others, we run it on virtual machines on OpenStack. So today we have around 18 petabytes of storage that is available. Around half of it is used, so we have a good leeway. We don't have that many cores. As you see, we are migrating more and more into Spark. So here the users decide what to do with their cores. At CERN, each project gets a certain number of cores, and they decide what to do. So as you will see that we are also provide a easy way to have these disposable Spark clusters, so they can create them, run a Spark analysis, and immediately use it for something else. So these are the components that we use, but some of them are very low usage. For example, Pig is very low usage. The main ones are for compute is mostly Spark and little bit of Hive, and for storage it's HDFS. For large scale analytics, and if you want like index kind of access, it's on HBase. And we also run a Kafka service, but I don't talk about it much. But that's how people get data into our systems. Okay, so what do we do in terms of deployment? So initially we started with CDH, so the Cloudera distribution for Hadoop. But recently we have moved to vanilla Apache, mainly because Cloudera was mixing things from different versions, and it is hard to know what we are running. And we also, the management was also not willing to get a support license from Cloudera. So we now mainly run it on Apache Hadoop. We still have 1 or 2 instances of Cloudera which will eventually migrate to vanilla Apache Hadoop. And we run it on CentOS. We do all the configuration management with Puppet. So when it comes to security, we use Kerberos, and it is fully integrated with our Active Directory. And we also have fine-grained authorization with integration with LDAP and eGroups. We run it in high available mode. So all these master services, whether it is name node or resource manager or HBase master, they all run in high available mode, because when the LHC is running, the system that relies on this infrastructure is highly critical. So that's why we run it in this mode. That means we can also do rolling deployment for some minor updates. We don't have to bring the whole service down. We also developed a lot of stuff to collect our data for alerting and long-term analysis. We also do backups of our HDFS data, so it's another custom-built solution. So we try to identify the new files that landed in our HDFS, and we ship it to our tape system that's called Castor. So why did we move to Apache Hadoop distribution? So it is better control of the core software stack. So we want to be a little bit independent from the vendor, and we can also pick some commits that we want and do our own compilation. So for example, we were early adopters of Spark on Kubernetes. So even before it was in 2.3, we were using it internally because if you are able to build it yourself, you have more leeway. We have developed everything this build platform internally. So if it's available, I can provide these details. Okay, next this is what is our data science platform. So we call it as Swan. So it is essentially Jupyter notebooks on demand. So this is developed at CERN. It is tightly integrated with our resources. So if you heard of Google Colab, so when you use something on Google Colab, you use a G drive to store your files. So when you use our Swan, we have our internal Dropbox-like thing, that is CERN box, where we store our files. And all the high energy physics software is also provided in the Docker images, and we also have a facility to offload the computation from the notebook to the Kubernetes cluster, or if it is a distributed computation, to a Spark cluster on Kubernetes. If you don't know about notebooks, so they're very good for early stage of analysis or late stage of analysis. It's mostly interactive. So you have a cell, you write a little code, and you execute. You have your output, and this is widely used at CERN because it's also a research organization. So there's a lot of trainings that are delivered using this platform. A lot of initial phases of analysis, like exploring your data, and the final phase of your analysis is actually done. But it is not used for, let's say, batch, because that's not the purpose. So if there is like a big ETL job to be run, we have a batch system for that. So we have also integrated these notebooks with, let's say, Spark and Hadoop. That allows users, if they can parallelize their computation, which is actually quite easy at CERN, because most of our data are physics events, and each event is discrete. So all the data for a particular event is in a single record. So each record can be processed in parallel. So most of the analysis are highly scalable, highly parallelizable, let's say. And it's web-based, so we don't have to manage things that people have to install. As I said, we have around 12,000 users at CERN who use our facilities. And this is how it looks if you are using, if you don't know how the Jupyter notebook looks like. So this is like a Spark SQL query. So what you get with the Jupyter notebook is your markdown, your code, and your visualization. So we have developed a Jupyter notebook extension. So if you are offloading a large computation to an external cluster, instead of showing a busy screen, we thought it's a good idea to show some information. So we have developed a extension that tells them at what stage it is, what is completed, and it also shows that number of parallel active tasks. So if somebody has done a static allocation of 200 cores, if he's actually using all 200 cores or not. And we also provide some troubleshooting tools from here, so that he knows a little bit. These are people who are, let's say, users of Spark. They are not experts. So our team is supposed to be, let's say, experts of some of these technologies. So when we say the integration of Jupyter notebooks with Spark, so as you know, Spark is a distributed compute framework, right? You have what are called drivers and executors. So all of them should have the same equalized environment across. So for this, we externalize our software into a read-only file system called CVMFS, and make sure that all of our executors and drivers all are using it. And you have seen one of the extensions that is called Spark Monitor. That is, all of our stuff is fully open source. I've put some GitHub links. You can try to use it if it is useful for you. And we have also developed what is called a Spark connector. So with a click of a button, you make a Spark session. So this means that people don't have to write any code for at least getting a Spark object. So why did we develop Spark connector? So initially, we just gave them a notebook and asked them to create their own Spark session. And we thought, and then we had many questions, and people were really confused what they have to do, how they can ship packages from the driver to the executors, how to inject additional Python modules and all these things. So we thought it's not a bad idea to take away all this configuration complexity from the users and hide it in an extension. So that's what it does. So when you click on the button, you can select a cluster, and then we also bundle some configuration depending on the projects. You say that, okay, this project needs all these 6 parameters all the time, so we just bundle it. And we also provide the flexibility to inject additional configuration and then connect, and they should have a Spark object at the end of it. And the second one that is also widely popular is this Spark monitor. So this is another Jupyter Notebook extension that allows for the live monitoring of the Spark jobs that are spawned from the notebook. And as I said, you can also access the Spark Web UI from here. These are actually, if you are using Jupyter Notebooks, these are very easy to install, these extensions. And they should work pretty much out of the box. And recently, we also developed yet another extension that we internally call it as Ket Selection. So this is to create ephemeral Spark Kubernetes clusters on demand. It's possible because internally we run CERN Cloud runs on OpenStack. So in OpenStack, there is an easy way through a component called Magnum to create Kubernetes clusters. So what this extension does is it checks if the user has privileges to create a cluster in these compute resources, and then amount of quota he has, and with a click of a button, he can create a Kubernetes cluster. And then he can also add a cluster that was created by another person, and he can also grant access from one user to another user, and also immediately attach the notebook to this cluster so that any of your Spark tasks can be offloaded to this. And this is also a Jupyter Notebook extension. This will mostly work if you are running OpenStack. But we also tested with gcloud, because as you can imagine, CERN is kind of restricted with the amount of compute that we have, the research. So there are also plans to go to some of the clouds like Telecom Cloud or Azure or AWS. So we're also, it's not fully ready. We also want users who have created a gcloud cluster to be able to use it from the notebook so that, everything is in one place. So this is the idea. And this is our, let's say, outlook. So it's always, all these things mostly, they are ready, but at the same time, they're all work in progress. So we want to integrate all the services at CERN with this, let's say, data science platform. So we have internal storage that's called EOS, and we have, let's say, the industry standard storage that is HDFS, and we have personal storage that is CERN Box. It's called it's named after, let's say, Dropbox. And we have the software that is also available from this, and users can use long-running clusters like YAR, or they can use Kubernetes. Of course, today it's only Spark, but with Kubernetes you could do a lot of things. So, for example, you can have your Airflow running on Kubernetes and things like this. So what you see Spark there, you will have our intention is we'll have multiple things going on there. So we don't see many users apart from the 3-4 big projects that we have using HDFS, because they are not actually responsible for collecting the data. Someone else is collecting this data, and it is kept in at CERN storage that's called EOS. But they do want to analyze data, and they do want to analyze this data with Spark, because as I said, many of the analysis is highly parallelizable, because each event is discrete, and a file typically has thousands of events. And since these people want to use Spark, so we have we are trying to, we don't want to use Spark and Yarn, because then you're going to waste your storage resources, right? So we just want to this cloud model of separating storage with compute. So this we run it on Kubernetes, but on top of OpenStack. We run it on top of OpenStack because that's like the CERN internal private cloud. And today we are targeting these users, like even if people have users that does some Spark streaming with Apache Kafka, they don't have to be on Yarn. They can just as well run it on Kubernetes. And then if they have high demand computing, so if somebody wants like 1,000 cores, so we cannot provision this on the physical servers in a few months, because CERN has a big process of procuring any equipment. So it typically takes 6 to 8 months to buy any physical hardware, because there is only 2 times a year the finance committee meets and signs off projects. So for them, these kind of things are very, very cool, because they can decide how to use their compute resources, whether they want to run Spark or they want to run, let's say, internal CERN batch system that's based on Condor. Okay, I just briefly tell you what are the big data projects we have at CERN, so that you have some understanding of how we are trying to use this. So the headline project that we have for our group is what we call CERN Accelerator Logging System. So these are the IoT logging data that is coming from thousands of devices that is in this LHC. It's a critical control system for calibration of a lot of things. There are radioactive cavities that accelerate the particles. There are superconducting magnets that orient the beam, and there are valves if there is a beam dump. So there's a lot of devices here, and these people decided together with us that the relational database is no longer serve the purpose, because the amount of data they're going to acquire is going to grow and grow. So today, in the past, it was like, I don't know, a couple of terabytes per year, but nowadays it can be up to 200 terabytes per year. And this is, let's say, a critical production system that we run in our service. The components that we run is obviously the HDFS and HBase. And we also provide the tools, the front-end tools for the programmers and the scientists, and the applications connect with their API. So we are not mainly into the picture, and they also land data into Kafka and then process them and store it into HBase and HDFS. And to reduce the latency, we write every second, but then there is also a compactor that compacts the jobs and keeps them in nice, reasonable sizes. As you can imagine, HDF is not very good if you have lots of small files. And this is another CERN IT monitoring infrastructure. So we get data, let's say, not only from our CERN data center. CERN also runs the grid. This is called HEP Computing Grid. So it's called WLCG, LHC Computing Grid, where there are a lot of grid services that produce logs. And those logs are also sent to Kafka, and then eventually they are also stored not only in HDFS, but also in Elasticsearch and InfluxDB, so that people have these nice graphical interfaces like Kibana and Grafana to just see a plot and get an alert, simple alerts. And if they want to have some long-term trending, so for example, this group, we have committed, I don't know, this amount of resources, but let's do an accounting and see, if they have used more or less. So for this kind of, long analysis, that's when they will use, Spark together with the data that is on HDFS. So in Elasticsearch and InfluxDB, the data is kept depending on the amount from 6 weeks to 3 months, but in HDFS forever. It's like an archive. Here the scale is not as big as LHC, because we are just talking about computers, the servers, which are like in thousands, not like more hundreds of thousands. Okay, so that is all about the infrastructure, but we also want to see if some of the industry tools can be used for the actual physics analysis. So this is how a typical LHC data pipeline looks like. So those are the pictures of the detectors for all the experiments. So they detect the path of the particles and collect this data and send. And we have there what is called data acquisition services. They do a lot of event filtering because we don't want to collect a lot of known physics, what they call known physics. So which means almost 90% of the data is filtered out. So when you are getting this volume of data, the filtering is typically done with hardware accelerators like FPGAs. And then whatever is filtered out is the remaining 10% is sent to the data center where the reconstruction happens. And then we have these huge data sets that are made available. And from the reconstructed data, also, there is a process called skimming. So essentially, to choose events based on, a run, based on the amount of energy and things like this. So that's what they do in skimming is essentially yet another filtering of the data, and they create a smaller data files. Those are called analysis objects. So today Spark plays a role in this skimming, which is like a big ETL. And then in the final step of analysis where you do interactive analysis on small analysis data objects, which are typically in 2 gig of size. Okay, so what is this CMS data reduction facility? Typically what they were doing before, CMS is one of our experiments, is they were running this skimming process 4 times a year. So people from this collaboration send the request for the data, how the data should be skimmed. So essentially specifying the filtering conditions, and it is done once a quarter. So it's not run on demand. So with this data reduction facility, with the help of Spark, what we want to do is, can we do on-demand reduction of data? It was done only 4 times a year because there was not enough, compute resources, and also the process to take skimming is little. At least it was a bit sequential. So with this data reduction facility, so we were trying to essentially, have a large Spark job to reduce 1 petabyte of data into hundreds of gigabytes. So we were able to do this with Spark. We were using, I think, around 2,000 cores, and it was done in 48 hours. We have a proof of concept available, even though we were managed to do the reduction of 1 petabyte data, but it is still in discussion whether they want to go ahead in this direction or not. Whether you do it with Spark or with something else, even with Spark, the number of CPU seconds is still the same. What you reduce is the wall time. Okay, so to do this, we had to develop some components. The physics data is stored in what are called root files. These are not Parquet files or ORC or any of these files that you guys generally know. And to load this root file into a Spark data frame, we had to write a Spark data source. So that is called the Spark root. So there is a link. And in addition, this data is not stored in HDFS or S3 where you have connectors available and you can access data. So this is stored in EOS, and it speaks, let's say, a scientific protocol called XRootD. So we had to extend HDFS and create this root:// protocol. So we had to write this so that we can directly access the data over XRootD protocol from Spark. Okay, that is the first part. So that was basically here in the CMS data reduction where the Spark was used for the offline processing. And for the physics analysis, most of the PhDs, what they do is they use an analysis package called root. So it was written in C++, but nowadays everybody is more comfortable to work with Python. So those guys have made a Python API for a lot of this C++ code they have. But now what we are trying to do is whether we can push, we can have like a multiple backends. So a backend that runs locally, a backend that can run in Spark. So essentially it's the same philosophy. So we build a DAG based on the projections and the filter push downs, and defining additional columns, and send this DAG to Spark for execution. So this is still in the experimental phase. The idea is to either send it to Spark, mostly on the Kubernetes. It is in the experimental phase because even though basic things work, if you know a C++ object, you also have your methods stored inside that. So some of those cannot be accessed now directly. So further work is going on to make sure that the R data frame, what we call, can run in the distributed fashion using Spark. And the way it runs is we take the full data set, and depending on the amount of events that we have, and the amount of compute that we can get. So these are divided into sub-ranges so that each of the Spark executor can run these particular ranges of the events. Our team is still a little bit in the beginning phase of the machine learning, but we had some initial prototyping for machine learning. So we are trying to see if Spark can help us in mostly on the feature engineering side, not on the model training yet. But even though we have used the model training together with what is called the Big DL from Intel with Spark, we are mainly trying to see if the initial phases where there is a lot of amount of data and the features that we want to extract from this data, whether Spark can help us or not. So there was also, my colleague has given a session at Databricks, so if you're interested, you can follow that. Okay, so what are the conclusions? So we see that there is a big demand for let's say industry big data tools at CERN. We have multiple critical projects in production. These are around the monitoring, and we also use it, I did not mention, for the security. To monitor what is happening in our networks as well. And we are in the early phases of using it for the physics data. We are part of the Hadoop and Spark service at IT, so we are kind of stable in some areas, like in the storage and things like that. But we are always trying to see. We are trying to evaluate whether Presto or Drill can help, some kind of a JDBC access from the storage systems. And because it's our research organization, we also spend a lot of effort in building a community. We deliver trainings on Spark and Hadoop, and we also write a lot of blog articles. So the link is here. So if you are interested, you can go through that. And if you are using similar technologies around the data science platform or the Hadoop tools, we are also happy to exchange experience and things like that. And most of the things I've put here are open source. If they are useful, you can use them. Okay, so that's all I have. So if you have any questions.
So I have two questions regarding Sparks over Kubernetes. The first one is, you said that it worked on OpenStack. Is it just because it's the only thing you have, or is it a technical limitation that you see?
It's not the technical limitation. We run OpenStack, so that essentially virtualizes our physical servers. So at the moment, we only run Kubernetes on these VMs. So we don't run Kubernetes on physical machines. You can run them. But it's an internal decision to optimize the resources and the configuration.
Okay. And my second one is, do you see specific usages of the people that are using Spark over Kubernetes? For instance, are they using them? Because you said that there was a limit in the cores that you could allocate, so this was a way for them to not use the Hadoop cores.
Yeah.
But do they? For instance, I was told that it was not very efficient to run small queries in Kubernetes because there is a startup time that is not efficient. So, in your experience, what are people doing with Spark over Kubernetes?
We try to ensure we have done a lot of optimizations, especially if you have very fat images and if you have to pull them, there is a higher startup time to start your executor and your pod. So we have some stuff that warms up our cluster so that what users need are always available. And in terms of answering your first part, so we have a lot of users nowadays using Spark on Kubernetes, mainly because their data is not in HDFS. So all the physics data is in CERN storage system that's called EOS. And they can only use Kubernetes to access the data. And we have few users from time to time because our Hadoop clusters are storage dense clusters. So the ratio between the amount of storage and cores is very high. So if we have like some ad hoc big analysis that cannot be fit, because we have, let's say, 40% of the cluster that's always occupied with some streaming jobs and some production jobs all the time. And if the analysis cannot be fit in the remaining 60%, we send them to the Kubernetes. And we are also planning to move more and more towards Kubernetes because this helps us to optimize the resources for various needs.
Okay. So you put in your data from Kafka to Hadoop, as you said, and so is this data for like offline analysis, or do you need it real time into Hadoop?
So the data is also required for real time. So the real time data, so we keep the data for the last 1 week in HBase so that it can be immediately accessed. And the same data is also kept in HDFS for offline processing. And we use Goblin. I don't know if you heard of Goblin. So we use Goblin to pump data both to HBase and HDFS. And the frequency at which it runs is configurable. Today it runs every 5 seconds.
Oh, every 5 seconds.
Yes.
So that's what my question is. So with Goblin, you run it every 5 seconds, right? And at your rate, like you would be creating a lot of small files with that, right?
Yeah. So we have a compact job that compacts all the small files into good enough size files every day, every night. We run this every night.
So how do your users get those?
So the users are hidden by our API. So our API, depending on the timestamp, will redirect them either to HBase or HDFS. So the users will never see these small files because the latest data is always in HBase and they go to HBase. And the HDFS, by the time the users see it, they are nicely compacted, and we kind of target around 2 gig size. But that's not always possible because there is some partitioning scheme, and some devices send less data than others and things like that.
Okay, so let's thank Prasanth.
Prasanth.
Prasanth. Okay, let's thank Prasanth also.
Yeah, thank you.